Hi guys, Sherlock's Apprentice here, aka Mike, and here finally I've got my latest video out. It's taken all 9 months to get everything together and finally presentable. So I hope you enjoy it. Does the moon's orbit debunk Newton's gravity? Quite a claim. Earlier this year, I saw a quote that the sun's gravitational attraction on the moon is over twice that of the Earth's gravitational attraction on the moon. This is the original three-body problem. It was actually in a Twitter chat with Simon Dan that he corrected me on my figures and he pointed it that it was 2.1 times stronger. So I decided to study the heliocentric data and historical records and check this claim and the three-body problem of the sun, earth, and moon for myself. Okay, what is the three-body problem? In physics, specifically classical mechanics, the three-body problem involves taking the initial positions and velocities or momenta of three-point masses and calculating their subsequent trajectory using Newton's laws of motion and Newton's law of universal gravitation. Unlike the two-body problem, the three-body problem has no general closed-form solution, and it is impossible to write a standard equation that gives the exact movements of the three bodies orbiting each other in space. Historically, the first specific three-body problem to receive extended study was the one involving the moon, earth, and sun, the original three-body problem. Here are two very simple force diagrams. In the top diagram, we can see that the 10-kilogram weight will make the seesaw lever go down and the 5-kilogram will go up. But in the bottom diagram, because of the distance between the fulcrum point, the 5-kilogram weight will go down and the 10-kilogram will go up. Let's see if we can get a pointer. Let's get a laser pointer. Okay, so because of the 3-meter distance there, there's greater force here than here. So we must consider mass and distance. Simple physics. Here is a very simple, not to scale obviously, illustration of the Sun, Earth, and Moon system if we viewed from above the orbital plane of the Earth around the Sun. I'm going to ignore the relative movements of the Earth and Sun in this demonstration because actually it only makes things worse for the heliocentric model. So we can see the Earth once a month orbiting the Moon, orbiting the Earth once a month. So as long as the gravitational attraction between the Earth and the Moon is greater than the gravitational attraction between the Sun and the Moon, then the Moon will continue to orbit the Earth. But what if this is not the case? Would the Moon still orbit the Earth? So how do we measure gravitational attraction, GA, between two masses? We use Newton's law of universal gravitation. Now, my maths is above average, but for these type of calculations, I needed help. So I used Math Solver to help me. And here's a link anyone can use. It's a free service. So I took the mass of the Earth, Sun, and Moon. Here are the data measured in kilograms, gravitational constant, the distance from the Sun to the Moon in meters, the distance from the Earth to the Moon in meters, and then here is the universal gravitational equation. Force is big G times the mass of the large object and the mass of the small object divided by the square of the distance of the two masses. So here, using Math Solver, putting in the G times the mass of the Sun times the mass of the Moon divided by the square of the distance between, and this is an average distance, we get this amount of newtons. The same I did for the Earth and the Moon, gravitational constant, the mass of the Earth here times mass of the moon divided by the distance. Again, an average distance of the moon from the Earth to give this newtons. So if we take the Newton's force of the Earth, sun to the moon, divide it by the force between the Earth and the moon, we can see that it's actually nearly 2.2 times stronger using the Newton's law of universal gravitation. Houston, we have a problem. Go back to our simple force diagram. We put force here of the sun against the force of the Earth, which is going to be the greater force. So let's look at the moon's orbit. So if we look at a full moon situation, the moon is far side of the Earth, away from the sun. We can see then full moon. Gravitational attraction force between the Earth and the moon, I've labeled X. See here? And the gravitational attraction between the sun and the moon then is approximately 2x. Here are 2.2, but just for this simple diagram, I've just used 2x. So then we go to third quarter, and we can see we've got conservation of momentum. So this moon is being pulled in this direction with conservation of momentum. This orbit makes sense. And then we've got the pull of the sun and the moon here still pulling in this direction. So yes, this orbit still makes sense, and the attraction here. So now at new moon, we have got an attraction between the moon and the Earth of X, pulling against a force double the size and a conservation of momentum this way. The net force here is in this direction. There is no force towards the Earth. So how is it possible for the moon to orbit the Earth? Since March of 2024, I've been studying this problem for a solution as to why the moon orbits the Earth by researching famous physicists, mathematicians, and astronomers. So Isaac Newton, including an English version of his Principia, Alex Clairaut, Leonard Euler, Joseph Lagrange, Jean d'Alembert, Henry Cavendish, Charles Eugene Delaunay, Henri Poincaré, William Hill, all have studied the three-body problem. I initially prepared reports on every one of these scientists, but decided to cut them from this presentation so it would not be so long and boring. Through all my research, I could not find a simple explanation for the sun, Earth, moon, and the three-body problem, but I think I know why. The masses of these celestial objects were unknown and varied. The following screenshots are from Brave AI search engine, and I asked for the historical masses of the sun, Earth, and moon. So first the Earth. Isaac Newton laid a foundation for calculating the Earth's mass using the law of gravitation. He estimated the mass of the Earth to be 6 times 10 to the power 18 kilograms, based on the force of gravity between the Earth and a person. Henry Cavendish conducted his experiments to measure the density of the Earth. From this, he calculated the Earth's mass to be approximately 5.48 times 10 to the power 18, so quite similar to Newton 100 years earlier. Pierre-Simon Laplace calculated the Earth's mass in the 1800s to be approximately 6 times 10 to the power 22, quite a bit larger. But today's calculation, standardized from the 1960s, is 5.9, nearly 6 times 10 to the power 24. You can see quite a bit larger. The moon mass historically. So in the 17th century, astronomers estimated the moon's mass to be around 50 times smaller or 100 times smaller than that of the Earth, 1 to 50, 1 to 100. 19th century, we've got Henri Poincaré and Simon Newcomb estimating between 80 times smaller and 60 times smaller. So based on Isaac Newton and Henry Cavendish estimates of the Earth's mass in the 17th and 18th century to be 6 times 10 to the power 18, then the moon's mass at that time would have been approximately 6 times 10 to the power 16, 100 times smaller. 19th century, using these calculations, it's about 7.5 times 10 to the power 21. 1970s, the Apollo missions and subsequent lunar landers, like NASA's lunar orbiter, further refined the estimate. The mass was determined to be approximately 50 or 40 times that smaller of the Earth's mass. So in 1970, the approximate mass of the moon was 3.67 times 10 to the power 21, where actually today the accepted figure is 7.35 times 10 to the power 22, or 81 moons equal the mass of the Earth. So it's 81 times smaller. So you can see quite a large difference again between Isaac Newton's time, when the mass was 10 to the power 16, 10 to the power 22. Then we come to the sun. Isaac Newton, in his work Principia, estimated the ratio between the Earth's mass and the sun to be approximately 1 to 28,700. However, this value was based on a faulty solar parallax measurement, which he later corrected to 1 to 169,282 in his third edition of Principia. I enjoyed reading Principia. Actually, I found, like I say, an English version printed, I think, in 18 something, and very interesting finds in that book. So Sir Isaac Newton believed the mass of the sun initially to be, like I said, 28,700. That would give the mass of the sun to be approximately 1.72 times 10 to the power 23, but adjusted to 1 times 10 to the power 24. Henry Cavendish measured the gravitational constant using the torsion balance, which led to an estimate of the sun's mass, although his value differed only by 1% of the modern value. It was not as precise. So Henry Cavendish calculated to win 1% of the current value of the mass of the sun, which is impressive, as he was 1 million times in error with regards to the mass of the Earth. Today's modern calculations have the sun approximately 2 times 10 to the power 30, or 330,000 times that of the mass of the Earth, which is more than double to what, or approximately double to what Isaac Newton was estimating. In the last 300 years, there's been no scientist, physicist, or mathematician that's been able to conclude on the three-body problem of the sun, Earth, Moon, because there's no consensus of the data regarding masses and distances. Only in the last 50 years has there been consensus of the factual data regarding the masses and the distances of the three celestial bodies. But with this data, we now have a major problem. Gravity doesn't work. And here's a reminder of the calculations showing the force being 2.2 times stronger from the sun. Another interesting fact in my research is the changes using the Wayback Machine in a three-body problem on Wikipedia in the last 20 years. 392 changes in total. Especially since 2015, there's been many changes. So I decided to compare some of them. And if you remember, it was around 2015, 2016 that Flat Earth started to really take off. 2016 is when I started to get interested in the subject. So the first entry, to April 2004, For the three-body problem, the Sun, Earth, Moon is considered a restricted three-body problem. I'll cover the restricted three-body problem later in this presentation. But you can see here, the circular restricted three-body problem is a special case in which two of the bodies are in a circular orbit and the third is of negligible mass, approximated by the Sun, Earth, Moon system. February 20, 2008. The Sun, Earth, Moon is still considered a restricted three-body problem. Here we have the first mention of the Hill sphere and Lagrangian points. The restricted three-body problem assumes that a mass of one of the bodies is negligible. The circular restricted three-body problem is a special case in which two bodies are in circular orbits approximated by Sun, Earth, Moon system. For a discussion of the case where the negligible body is a satellite of the body of the lesser mass, see Hill sphere. For binary systems, see Roche lobe. For another stable system, see Lagrangian point. In November 2015, the layout changed Wikipedia. So this was the new layout. And they just had a simple reference of the three-body problem. Receive extended study was the one involving the Moon, Sun, and Earth, but no details. February 2024, so we're coming to this year. Wikipedia page now starts to note that there's no general closed-form solution to the three-body problem. So here, unlike the two-body problem, no general closed-form solution exists. This is in February 2024. This year. As a resulting dynamic system is chaotic for most initial conditions and numerical methods are generally required. So here again, the same sentence being put left in regarding the Moon, Earth, and Sun. Now, what it means by numerical methods is during those years I studied the scientists, although they may not have had the mass is correct, so therefore we're not measuring regarding gravitational attraction. What they were trying to measure was produce tables and data for celestial navigation, where in the sky the moon would be. So there were all of those scientists basically were coming up with differential equations to be able to calculate the position of the moon. May 2024, the next change is the only way to predict the motions of the body is to calculate them using numerical methods. Just as I said, this agreed with my studies in the mathematicians 18th and 19th centuries. I jumped ahead there. Here it is, says the only way to predict is using numerical methods. June 24. The next addition is that it is impossible to write a standard equation that gives the exact movements of the three bodies orbiting each other in space, which is the quote I gave at the beginning of this presentation. So I must have done that around June. There it is. It's impossible to write a standard equation for a three bodies orbiting each other in space. And it still says three-body problem is a special case of the n-body problem, which is multiple bodies more than two. Historically, the first specific problem received extended study was the one involving the Moon, Earth, and Sun. So they still keep mentioning that this is a three-body problem. July 24. Wikipedia changed the wording and removed the word impossible, but still point out the system is chaotic. So it's funny that it was during that time that I picked up the word impossible. And then when I went back to research it again, it was, where's that word impossible gone? And then I realized it was around July they changed Wikipedia page. See, the system is chaotic and the only way is to predict using numerical methods. September 2024, the wording has changed once again, and this is the same as the current page on Wikipedia as the last week, as I last checked. Because there are no solvable equations for most three-body systems, the only way to predict the motions is to estimate them. So they've changed it that there are some three-body systems that can be calculated, but most of them cannot. In 2013, there have been advances in discovering periodic solutions for three equal point masses as shown here. As of today, no one has managed to model the sun, earth, and moon as a periodic three-body problem. So all of these shown here, 20 of them, they've been calculated using computers, and all of these masses are equal. So there is not a difference in mass. And you can see not one of these resembles planets, moons orbiting a sun. I suppose you've got this situation if the objects were opposing the sun and orbiting each other. This one's similar down here. But other than that, there's very little resemblance to planets orbiting. So what do the scientists of today, like Neil deGrasse Tyson, etc., say to explain this problem? The moon is in with the Lagrange points. The moon is within the Hill sphere. The moon is a restricted three-body problem. I've seen videos of Neil saying that. So the Lagrange points are 5 unique points in space discovered by Leonard Euler, L1, L2, L3 in 1767, and Joseph Lagrange, L4, L5 in 1772. These points require a third mass to be virtually massless relative to the other 2-point masses. This works perfectly for satellites and telescopes, space shuttles, like or the telescope like the James Webb Telescope, which is positioned at L2, and it's in a halo orbit, which I found interesting research and how that works. But the Lagrange points are all restricted three-body problems. So the Euler discovered that there were a three-body solution to the Earth, Moon, and Sun, but it required that the third object to be massless and direct in line with the Sun and the Earth. Hence, we have L1, L2, L3. Lagrange worked out that you could get two more balanced three-body problems using equilateral triangles, and that is where L4 and L5 come in. The Hill sphere by William Hill in the early 1900s is a three-dimensional representative sphere showing the gravitational field in relation between two celestial objects. This usually between the sun and a planet. You can also have a Hill sphere between the planet and the moon, so using two objects. But when you check the calculations of the Hill sphere, you discover that it requires an assumption that the third mass needs to be treated as massless in the calculations. So the Hill sphere theory works for satellites and space telescopes, but not applicable for moons with a proportionate size to the planet it orbits. This is another restricted three-body problem. So if you have a satellite within the Hill sphere of the Earth here, it will be attracted to the Earth, or it will orbit the Earth. It will not be affected by the sun. If it is outside the Earth's Hill sphere, you can see here, then it will be affected. It will be pulled towards the sun. And similarly, when you start going out to here, this is showing you a gravitational field rather than just the 5 Lagrange points. That is what the Hill sphere is. What is the restricted three-body problem? Is the sun, earth, moon a restricted three-body problem? The restricted three-body problem, the simplest form of the three-body problem, is called the restricted three-body problem, in which a particle of infinitesimal mass, that wasn't easy to say, moves in a gravitational field of two massive bodies orbiting according to the exact solution of the two-body problem. The particle with infinitesimal mass, sometimes called a massless particle, does not perturb, i.e. move, the motions of the two massive bodies. There is an enormous literature devoting to this problem, including analytical and numerical developments. Okay, I won't read the rest of it. You're welcome to. So the Earth orbits, as the moon orbits the Earth, right? Actually, it isn't actually a little bit more complicated than that. The moon is circling a point about 3,000 miles from our planet's center, just below its surface. Earth is wobbling around that point too, making its own circles. That spot is the Earth-Moon system center of mass, known as the barycenter. It's the point of an object or system of them at which it can be balanced perfectly with the mass distributed evenly on all sides. And I found this very nice illustration that you can watch the Earth wobbling as the moon is orbiting, and here the green star is the barycenter, seeing it in two planes. If the third mass is of infinitesimal mass, massless, such as a satellite, then the restricted three-body problem can be solved. So any satellites or large telescopes or even space shuttles are relatively massless compared to the mass of the Earth. But because the mass of our orbiting moon on the Earth makes the Earth wobble by 3,000 miles from its center, the Sun-Earth-Moon system cannot be considered a restricted three-body problem. To finish this presentation, I watched a great video on YouTube by .physics, who wrote a program on Python to demonstrate the three-body problem and how to solve it. Here's a link to that video. I'll also put a link of the video and the code. He gives a link to the code. Unfortunately, my knowledge of coding is limited. I'm struggling to enter the masses and distances for the Sun, Earth, Moon with the correct units. But for anyone with basic coding experience, I'm sure this is a no-brainer to prove the moon can or cannot orbit the Earth. And when you use this Python, it gives you a visual demonstration of the system. Now, because of the distances, I think that will be difficult even to scale. But if somebody wants to try it, they're more than welcome. So I tried desperately to find somewhere in the history books and the science literature an explanation as to why the moon is able to orbit the Earth with the sun having twice as much gravitational attraction. I've heard people say, oh, it's similar to Pluto and Charon, like two objects orbiting each other, and those two objects then orbit the third, the sun. I looked into that, and that you cannot compare this with the Earth and Moon. One, because of the proximity of the Pluto and its large moon, and the gravitational attraction between them is 40 times stronger than Pluto's attraction to the sun. So I'm still waiting for satisfactory evidence. People keep saying to me, oh, it's simple, but you need to take all the differential equations into consideration, the movements, and well, it's very simple. An orbit can be elliptical, okay, but it cannot be a bumpy road, i.e. the moon cannot 13 times a year keep falling away from the sun to successfully orbit the Earth. So that's the conclusion I found, that what we see, the moon, sun, and Earth, debunks the gravitational equation, the apple falling to the Earth and then the moon falling to the Earth does not seem to be the same. So Isaac Newton. So thanks for watching. See you on the next one, guys.